Thank you very much. Indeed, it's a big pleasure to speak at this seminar. I'm going to speak about Birational involutions of the projective plane, which is a very classical object, in fact. So I start with the main definition. You probably heard about this object before, the Cremona group of rank n over a field K. This is just the group of Birational automorphisms of the projective n space over the field K. In algebraic language, well, this group has a purely algebraic interpretation. This is just the group of automorphisms of the function field in n variables over K. I start with giving some examples of Birational transformations, and I start with a very famous example of a standard Cremona involution of P2. This is a very explicit Birational map, which is given by the formula you see here. XYZ goes to YZ, XZ, XY. If you divide by XYZ, then you easily see that this is actually an involution, right? And you can see that it's not defined in 3 points, namely 1, 0, 0, 0, 1, 0, and 0, 0, 1. So in what follows, I will denote by int of sigma the indeterminacy locus of a Birational map. So what are other examples? Another example, for example, well, it's not a very interesting one, but still, it's the group of all biregular transformations of P2, which is isomorphic to the group PGL3 of C. This is clearly a subgroup of the Cremona group of rank 2. And in fact, there is a very classical result, which is called the theorem of Noether and Castelnuovo, an old one, an old result, which says that actually over the field of complex numbers, the Cremona group is generated by PGL3 of C and this standard Cremona involution, the involution sigma. Okay. And in fact, from this Noether-Castelnuovo theorem, you can deduce, well, with some work, that the Cremona group over C is generated by involutions. Okay, so it's generated by elements of order 2. So, okay, this was the story over the complex numbers. Let us now vary the base field, and say that we work, for example, of the field of real numbers. Then one can ask the following question: is it true that the Cremona group of the real projective plane is again generated by biregular maps, by biregular automorphisms, and this Cremona involution sigma 0 standard quadratic map? Well, let's see. So here's an easy observation. If I have a Birational map, which is a composition of linear maps and my sigma 0, my standard Cremona involution, then its indeterminacy points are actually real. They're defined over the real numbers. Basically because, well, linear maps have no indeterminacy points and sigma 0 have only real indeterminacy points. Okay. Now let's look at the following Birational map, which I denote by sigma 1. It sends xyz to y squared plus z squared, xy plus xy and xz. It's not difficult to see that it's indeed a Birational map, a Birational automorphism of the projective plane of the real numbers, but it's not defined in some complex conjugate points. For example, in 0, 1, and plus minus I. Okay, so this implies, of course, that the Cremona group of the real numbers, actually cannot be generated only by linear maps and this standard Cremona involution. Okay, so then we have a natural question: do we have actually a nice set of generators? And 10 years ago, okay, so no, before giving the result, I need to introduce another class of maps. So okay, we learned that Cremona 2 over R is not generated by involution, it's not generated by sigma 0 and linear maps, right? Let me give you another example of a Birational automorphism of P2. This will be a geometric example, actually. So I start with 6 points on P2 in general position. So in fact, I take 3 pairs of complex conjugated points, P1, P1 bar, P2, P2 bar, P3, P3 bar, okay? I assume that they do not lie on the same conic. And I blow up these 6 points. Then, as everyone knows, when you blow up 6 points on P2 in general position, you get a smooth cubic surface in P3. Okay. Now you have strict transforms of conics, which passed through 5 of the 6 points that I blow up, right? Then I can construct these 6 curves back to P2. This is some Birational morphism. And the composition of these 2 maps, so the inverse of F and G, is actually a Birational automorphism of P2, which I call, well, following some authors, I call a standard quintic transformation of P2. It's actually a map of degree 5. You can compute it in coordinates. And now there is a theorem of 2012 due to Jeremy Blanc and Frédéric Mangolt, which says that actually the Cremona group of the reals is generated by PGR3, again by linear maps, sigma 0, sigma 1, which are given above, and the family of standard quintic involutions. Standard quintic transformations. It should be here in transformations. And the standard quintic transformations. So we see that when you go to the field which is not algebraically closed, you have a more complicated set of generators. From the theorem of Blanc and Mangolt, you actually can deduce that of the reals, Cremona group is again generated by involutions, by elements of order 2. And then I believe that there was a question of Dolgachev at some point, who asked whether it's true that the Cremona group of rank 2 is always generated by involutions. And actually, this turned out to be true. This is a very fresh, very recent theorem of Stefan Lamy and Yuda Schneider, who proved that over any perfect field, the Cremona group of rank 2 is generated by involutions. And the way you prove this theorem is, well, you really need to use, well, you don't need to use, but it seems that the way in which we can prove it today is via a so-called Sarkisov program. So it's a very important tool in the modern Birational geometry. So in dimension 2, it's actually, well, I would say quite classical and well established. It goes back to the works of Iskovskih and Gizatulin and again Sarkisov. So we have in dimension 2 a very detailed description of Sarkisov links. These are kind of elementary Birational maps, which you can use to decompose any Birational map between Mori fiber spaces in dimension 2. And maybe I will say a few words about this in the end of the talk. So the proof is really somehow it uses modern techniques. Good. So I proceed with more examples of Birational maps, more examples of Birational automorphisms of P2. So let me start now with P2 and take 7 points, again in general position. and consider the linear system of cubics passing through these points. I call it L. Then this is actually a two-dimensional linear system. Okay, so now take a point P in P2, again a general point, and consider all elements of L which pass through P. Okay, all the cubics passing through P. So we all know that actually the pencil of cubics has 9 base points. Okay, so I can define a map which sends a point P to the point which I call gamma of P, and by definition this is exactly the 9th base point. So this is a very geometric description of the birational map. Well, actually, of course, you should prove that it's a birational map, right? But you can do that, and you can prove that you actually can even compute the degree of this birational map. I think its degree is 8. It's a map of degree 8, and classically, it's known as the Geyser involution of the projective plane. This is the Geyser involution of the projective plane. All right. So this is an example of a Geyser involution. There is a similar example of what is called Bertini involution. Again, I start with 8, this time with 8 points in general position on P2. And I consider the pencil of cubics passing through these 8 points. Okay? And let P9 be the 9th base point of this pencil. Sorry. Let P9 be the 9th base point of this pencil. Again, take a general point on P2. There is a unique cubic in my pencil passing through P. And I'll define a map which sends P to the point which I call beta of P. And by definition, this is minus P, where this minus is taken with respect to the group law on the cubic C of P. Should be not a calligraphic button, just normal C of P. And in this group law, I declare that P9 is my 0. Okay, is the 0 in my group law. And again, you can show that it's a birational involution of P2. You can compute a degree. It's of degree 17, I believe. And it's classically known as the Bertini involution of P2. So these are two very, very geometric examples which were known to the classics of the Italian school of algebraic geometry. So why I'm giving these examples to you is because actually I have a theorem of Bayle and Beauville. Not an old theorem actually. Theorem itself, I would say, it goes back to the work of again of the Italian school, probably to the works of Bertini himself. But of course, at that time, people were not really able to prove theorems somehow strictly, and many proofs were incomplete. And Bayle and Beauville gave the modern classification of involutions in the monogroup over the C, over the complex numbers of rank and in dimension 2. Namely, they prove that every involution in Cremona 2 over C is conjugate to one of the following. So of course we have linear involutions of P2. In fact, basically just one. Further, we have Geyser involution. Then we have Bertini involution. And the last class is so-called de Jonquière involution. Again, you can give a geometric description, purely geometric description of these involutions in terms of linear systems, but I prefer to give it just locally in coordinates, in affine coordinates. It just works like this. It sends xy to x px over y, where px is a polynomial of degree of odd degree to g plus 1. Then g is called the genus of the Geyser, of the de Jonquière involution. And that's it. So the claim is that every involution in P2 of P2 over the complex numbers is conjugate to one of these 4 involutions. Okay. In fact, well, I say 4 involutions, but rather I should say 4 types of involutions, because in fact, Geyser, Bertini, and Degenker involutions, they have moduli. They have these are actually families of involutions. We will see later. We will see later what parameterize actually these involutions, these families. Okay, but I would like to explain actually, well, at least briefly, the strategy how we can prove the Bayle and Bayle theorem. To prove this theorem, we basically, in fact, before I should have said probably that every involution in Cremona 2 is conjugate to one and only to the one of the following. Okay. So I would like to explain then actually 2 things. First, why every involution is conjugate in Cremona 2 over C to one of these 4. And second, why these involutions are actually different. So why, for example, the Geyser involution is not conjugate to a Bertini involution. This is absolutely not obvious. Why I cannot have a, when I say conjugate, I mean just in usual group theoretic sense, like why there is no Birational map in P2 which conjugates Geyser involution to the Bertini involution. So I'm going to explain these 2 things. Okay. And I start with the first thing. And the first thing is directly related to the theory of rational G surfaces, which was, well, today you can view it just as a part of minimal model program. Just an easy case of dimension 2. I think the theory in the case of any base field, of any perfect field, goes back to the works of Manin and Deskovsky, back to 70s probably. Nevertheless, let me just briefly describe this theory, describe this strategy to classification of finite subgroups in Cremona group of rank 2. Okay, so now you can assume that actually the field is any perfect field, doesn't matter. And although my goal is to discuss involutions, at the moment you can assume that G is any finite group, doesn't matter. So for any finite group of the Cremona group, there exists a k-rational smooth projective surface X, and the embedding of my finite group into automorphism group of this rational surface, such that, well, if you take the map, say psi, G-querent map psi, which establishes Birational isomorphism between X and P2, then G satisfies this equation here. So basically what you do is just lift your finite group of Birational automorphisms from P2 to the group which acts by biregular automorphisms of some k-rational surface. And for natural reasons, this procedure is called a regularization of the G action. So we replace Birational action of the group by a biregular action of the group on some k-rational surface. Okay, and of course, once you have a k-rational surface X acted by finite group G, then you can take again a Birational map from X to P2, and this gives you an embedding of G into the Cremona group of rank 2. Okay. So the more and moreover, so okay, we have this regularization, but moreover, it's not difficult to show that 2 subgroups of the Cremona group of rank 2 over K are conjugate if and only if the corresponding G surfaces are G-birationally equivalent. So now I work in the category of G surfaces, G-birational maps, and I consider my surfaces up to G-birational automorphisms, up to G-birational equivalence. Of course, actually, it doesn't matter. It's not important that I'm in dimension 2 exactly the same strategy works with in any dimension actually. I just try to keep it simple, but you can regularize groups of Birational automorphisms, finite groups of Birational automorphisms in any dimension and get the regular action on some bonifiber space, etc., etc. But for simplicity, let's keep it simple. We work in dimension 2. So okay, we have this bijection. We have this correspondence between conjugacy classes of finite subgroups of Cremona 2 over K and Birational isomorphism classes of smooth K rational G surfaces X, G. So G surface will be, for me, just a pair XG, where X is a rational surface, projective one, smooth one, and G is a finite subgroup of its group of biregular automorphisms. Okay. Good. So this is not a difficult statement, actually, this regularization in dimension 2. It's quite elementary. Okay, so we have this Birational isomorphism class of smooth K rational surfaces. Of course, using the methods of minimal model program, we can choose a minimal representative in this Birational class, right? So we actually have correspondence between conjugacy classes in Cremona and Birational isomorphism classes of smooth K-rational minimal G surfaces. Okay. And again, minimal means exactly the same as in a minimal model program, but everything G equivalently. Okay, we work in G equivalent category. All right. So why is good? Why is it good? Why is it useful to have this correspondence between? Because actually, K-rational minimal G surfaces are completely classified. This is well, again, it goes back to the works of many authors, but maybe in the most general form, it was proven by Skovsky, who discovered that if you have any perfect field K and X, G minimal surface, which is rational over the closure of the K over the algebraic closure of the K, so X is geometrically rational, then actually we have only two cases. So either X admits a conic bundle structure such that equivalent Picard group is Z2. When I say okay, or X is a Delpezza surface with equivalent Picard group Z. Okay, so these are just two-dimensional G-Mori fiber spaces. And that's it. By the way, when I say Picard group of X, I mean Picard group of X as the variety defined over the field K. Okay, so a standard fact is that if X has a K rational point, then this Picard group, equivalent Picard group, just a Picard group of X, is the same as the invariant Picard group of X K bar, invariant with respect to the action of the Galois group. Okay, K bar over K. So you can view this condition here, for example, that Picard X, the invariant Picard X of is Z. You can also translate it as follows: that when you take the invariant Picard with respect to the action of two groups, G and the Galois group of the field, then I get Z. Okay. Okay, so the conclusion of this small discussion is the following: that classification of finite subgroups inside of the Cremona group up to conjugacy is equivalent to Birational classification of the pairs XG, where X is as above, as in Skovsky theorem. But moreover, of course, since I'm interested, well, Skovsky theorem somehow does not assume K rationality of my surface. And if I want an embedding in the Cremona group of the Cremona group over K, then of course I have to work with K rational surfaces, right? This condition is automatically satisfied over the field of complex numbers, but over other fields, this is really some extra condition, and you should care about it. You should investigate not just any Delpezzo surface, for example, acted by a finite group, but the surface, the Delpezzo surface, which is k-rational over your base field. This leads somehow to some interesting questions. All right, so I will not explain the whole proof of Bayle theorem. Let me just explain some parts of it because, well, it will be useful for me later. So when I apply this program, the one that I described over the field of complex numbers, I can get indeed the proof of the theorem. Let G be now a group of order 2, so generated by an involution tau. Then you can show, it's not difficult to show just directly, that basically using some intersection theory, that you can, well, you remember we had two steps, not two steps, but somehow two parts. We can regularize the group on a Delpezzo surface, or you can regularize a group on a conic bundle. And in fact, if you regularize the involution on a Delpezzo surface, then you can prove that you can have only two cases. Of course, with the assumption that the group acts minimally, so the equivalent Picard is Z. And these two cases are Delpezzo surfaces of degree 2 and 1. So if you have a Delpezzo surface degree 2 with an action of the Geyser involution, I recall you that any Delpezzo surface of degree 2 is a double cover of P2, which is branched over a smooth quartic curve in P2. And then actually the Geyser involution, the involution that we saw before, is exactly the Galois involution of this double cover. Okay. And indeed, it acts minimally. It indeed acts minimally on a Delpezzo surface of degree 2, so the equivalent Picard is indeed Z. And the second case that you can have is Delpezzo surface of degree 1. And again, I recall you that Delpezzo surface of degree 1 is a double cover, again, -2 anticanonic, -2 Ks gives you a double cover from S to Q, where Q is a quadratic cone. And this morphism is branched along the sextic curve. And again, the Bertini involution, you can show that the Bertini involution is exactly the Galois involution of this double cover. And that's it. These are the only two cases that we have for Delpezzo surfaces. Now you remember we have Degenquier involutions. They are actually regularized on conic bundles, but I will not discuss this. So I just want to illustrate the Delpezzo case because I will actually use it. I will use it later. Okay, so that was the first part of the proof. Somehow I want to show that every rational involutions of P2 over C is regularized on some rational surface, and we actually can show that it's conjugate to one of the involutions that I gave you in the Bayle theorem. So I have these 4 classes. Now the second question is actually why these 4 types are different. So why, for example, like Geyser involution is not conjugate to Bertini involution. So to prove that, we can use a very useful invariant. So assume that I have 2 surfaces, S and S prime, acted by involutions, tau and tau prime. Okay, and assume that I have actually a conjugating map from S to S prime, say phi. Now you can look at the curve on S, which is fixed by C. Then you notice that the conjugate involution, tau prime, fixes the proper transform of C, which is isomorphic to C. So I can define the following set at the moment. So let's say F tau. That will be just a union of all curves which are fixed by tau and which are not rational. Because, well, not rational, it's clear why we have to assume that, because Birational map can contract construct actually rational curves. So I consider only non-rational curves. Maybe I should take normalization, but let's keep it simple. Let's just consider this union, and this is an invariant of the equivalence class of tau. And now I claim, as you can guess, that actually for these 4 types of involutions, linear, Geyser, Bertini, and doesn't care, this invariant is different. So if tau is linear, then the fixed curve is P1, this is clear. If tau is the Geyser involution, then f tau is a non-hyperelliptic genus 3 curve. You can guess which one. Actually, it's just a plane quartic. You remember that the Pellet surface of degree 2 is a double cover of P2 ramified along the plane quartic curve. It's a genus 3 curve, and it's important that it's not hyperelliptic. Second, if tau is the Bertini involution, then f tau is a genus 4 curve of degree 6. And finally, if tau is the Dejoncquer involution, then, well, I just remind you of the explicit formula, which defines the Dejoncquer involution. And you can easily see that the fixed curve is hyperelliptic curve given by this standard equation y squared equals px. Okay. So indeed, we see that our 4 types of involutions are different, so they're not conjugate to each other. Okay, so far so good. In fact, this correspondence, which from conjugacy classes of involutions to isomorphism class of the fixed curve. So I take an involution, consider its fixed curve, and then the conjugate involution, they have the same curve, the isomorphic fixed curves. In fact, this correspondence, it's bijective, okay? So there is actually a one-to-one correspondence between conjugacy classes of Geyser involutions and isomorphism classes of non-hyperelliptic curves of genus 3, conjugacy classes of Bertini involutions and isomorphism classes of non-hyperelliptic curves of genus 4, as well, special ones whose canonical model lies on a singular quadratic, Dejoncquer involutions of degree D, and hyperelliptic curves of genus D-2. So this is what I meant when I said that these involutions, they had moduli. Okay, so these are exactly these involutions parameterized by these curves mentioned here. So Gaussian involutions parameterized by plane quartics, for example. Okay. So that's it for the Bayle-Bayle theorem. It's kind of the sketch of their classification. That was, again, I want to stress that was the story of the field of complex numbers. Now you can, of course, ask what happens if I replace the field of complex numbers with any other field. Well, I will not replace the field of complex with any field. I will actually replace it with the field of real numbers. And in the second part of the talk, I will report on a joint project with Ivan Cheltsov, Frederick Mangolt, and Susanna Zimmerman. It's still in progress, but it's quite close to the end, to finish. And in this work, we actually classified involutions in the Cremona group of the reals, of the field of real numbers. So as you saw in the very beginning of this talk, when you go already to the field of real numbers, life becomes quite complicated. So, for example, in terms of you need much more. You need a lot of generators, not just standard Cremona map and PGS3 of C. So it's indeed a tricky thing. It's indeed an interesting question. So before discussing our results, let me just give you some maybe historical remarks, just how to finish the discussion of part 1 of this talk. So in fact, the strategy that I gave you, the theory of G surfaces, is allowed to classify all finite subgroups of the Cremona group or the field of complex numbers, not just involutions. But it was a series of papers published, which started with the work of Beauville and Bayle on involutions. But then there was a paper of De Vernay, who classified elements of prime order incremental over C. Then there was a work of Jérémy Blanc, which classified abelian subgroups of incremental over C, and probably the most complete work of Dolgoshev and Eskovsky, 2006, who classified basically all subgroups of incremental over C up to conjugacy. There are still some small open questions, I think, in this classification, but it's pretty complete, I would say, and well, it's quite impressive. It's a long paper of 100 pages. So the classification is really involved, and it's not really, it's not even in the paper, it's not very precise. It's rather a sketch in some places. Okay, so the question over C is actually completely solved. And in fact, I classified groups of some, I got some, actually big part of classification of finite subgroups of the real numbers. Namely, I classified groups of odd order, incremental over R, and groups which are regularized on real Delpezzo surfaces. So kind of half of classification. Remember, we have Delpezzo surfaces and conic bundles. But actually, it was quite clear, well, at least to me from the very beginning, that classification of involutions and then the classification of group acting on real conic bundles is quite a subtle thing. In fact, already involutions is a very subtle thing. And when we started to work on this classification of involutions, well, somehow the work in hypothesis, our first assumption was that it might remind the classification of Bayle by Beauville. It should be maybe similar, but life is not that simple. It turned out to be completely false. So classification of involutions incremental over R is quite sophisticated, I would say. So, well, first we have a bigger list actually. You remember over C we had just 4 types. We had just 4 types. Over reals we have well, I don't know. I don't want to tell you how many types exactly we do have, because it's still work in progress, and we'll try to get the refinement of our classification. But it's at least somehow it's at least 10 types. Let's say like that. But the most important issue of this classification is that this fundamental correspondence between isomorphism types of the fixed curve and conjugacy classes of involutions actually fails. So there is no so the isomorphism type of the fixed curve does not determine anymore the conjugacy class of the involution. And to be honest, at the moment for us it's not even, well, we try, you know, when you work with real algebraic curves, and in this case of course our fixed curve is real, when you work with real algebraic curves there are different properties of real curves that you can investigate. You can look at the real locus, for example, of the curve, and try to play with that. But it turned out that you cannot really somehow fix this correspondence. There is no way. So you cannot add some extra conditions, for example, for your real curve, so that this correspondence works. So I'll try to illustrate this phenomena, this issue, on a very, well, for me, it's a very interesting example, maybe one of the most interesting examples from our work. This example actually goes back to the work of Sophie Kovalevsky. So in the last part of the talk, I will talk about something which we called Kovalevsky involutions. Okay. So what is a Kovalevsky involution? Let me again come back to the Delpezzo surfaces. So let S be a complex Delpezzo surface of degree 2, now over any field, but I will be interested in complex numbers and real numbers. Then S is a double cover of P2, again ramified along the smooth quartic curve B, and we have the Galois involution of this double cover, which is called the Geyser involution. Okay, and now let's consider the group G of order 2 represented by involution tau, which acts on S. So now it's not I think it's an easy exercise to prove that when you work with complex delta surface degree 2, then the minimality condition is this one, that the picard of S equivalent 1 is Z. Automatically implies that tau is the Geyser involution. Basically, you just can compute the action on the -1 curves and see that it should act as a Geyser involution. Okay. But this really uses the fact that my surface is complex. When I go to the field of real numbers, the minimality condition becomes the following: that the picard of complexification of S, I consider the complexification of S. Okay, I consider its picard group. On this picard group, I have an action of G and the Galois group of order 2, the Galois group of C over R, and I require that the invariant part is Z. Okay, and this is indeed some extra condition. It's a different condition actually, and this leads to the following fact: that if you go to the field of real numbers, there are other involutions, there are other group G, which satisfy this minimality condition. So okay, so G doesn't have to be the Geyser involution. Let's see why. So to see why, let me maybe make some historical. Let me give you some historical background. So Sophie Kovalevsky, she was a student of, I believe she was a student of Weierstrass, and in one of her works, so she was interested in basically in analysis and in the problem of reductions of abelian integrals to elliptic integrals, and in one of her papers, published maybe in Corel, I don't remember, she proved the following theorem. A theorem which is given here below. Okay, I took it from the work of Kuvata, and I guess it's just a modern form of what Kovalevskaya actually proved. Okay, so you see it's kind of a statement from analysis, but there is hidden geometric condition in this statement of Kovalevskaya. So namely, there is some quartic curve occurs which somehow participates in the definition of this abelian integral, and the statement is basically that you can reduce this abelian integral to an elliptic integral using the change of variables of degree 2 if and only if this curve C, this quartic curve C involved, satisfies a very, very explicit geometric condition. So namely the condition is that it has 4 double tangent lines meeting in one point. I remind you that a quartic curve in P2, it has 28 bitangents, right? And among these curves, there are curves which satisfy a very special condition, namely that there are 4 bitangents which meet in one point. And implicitly, Kovalevskaya proved in her paper that it happens when you have an involution of P2, which leaves your quartic invariant, and which has an isolated fixed point, the point which does not belong to the curve. Okay, so this is the statement from above on the slide. So I have a smooth quartic curve in P2, then its 4 bitangents meet at one point if and only if there exists a algebraical involution of P2 which leaves B invariant and has this point Q as an isolated fixed point. Good. So, and then we used this statement of Kovalevskaya to prove the following. So now let me call this pair B kappa, so quartic plus involution of P2, the Kovalevsky pair. So after changing some coordinates, you can assume that kappa acts as follows: xyz goes to x minus yz. Then, of course, if you want an invariant quartic curve, then your curve will take a very special form. Okay, so assume now that B is given by the equation f for xyz equals 0. And then we prove the following. So if you have now a real delta surface of degree 2 S acted by involution tau, and this involution tau is not the Geyser involution. It's not the Geyser involution. It can be the Geyser involution, but it's not. Assume that it's not. And assume that the fixed curve is not empty. Then we can choose coordinates in P2 and in the weighted projective space. I recall you that the delta surface of degree 2 it lives in the weighted projective space 2, 1, 1, 1, 1, and there it's given by the equation w squared equals f4, where w is of course the coordinate of weight 2, and f4 is the equation which defines my quartic. So there exists coordinates in P2 and the weighted projective space, such the involution tau is given by the following formula. So it's basically just a positive lift of the Kovalevsky of the involution on P2. So of course, when you have this involution on P2, xyz goes to x minus yz. You can leave it to the double cover in two ways. You can, for example, put the minus sign before w. But we claim that actually tau is the positive lift. Okay, and moreover, well, I told you that the quartic B is very special, as you can expect. But it's not even special, it's even very, very special, in the sense that we know exactly what is the real locus of this this quartic. Actually, I could give you the equation, we have the equations, but it's a bit maybe it's not that useful. But you know that the real locus consists of either one oval or two nested ovals in P2. And then in the first case, the topology of the surface, topologically, the real locus is just a sphere. And in the second case, it's a torus. And in both cases, the fixed curve is actually an elliptic curve. You can indeed compute it just in coordinates. So what I would like to stress here is that maybe you know that plane quartic curves, well, there is the whole industry with people working on the topology of real algebraic curves. And you remember, when you consider its real locus, the real locus of real curve, it's kind of a bunch of ovals or lines, pseudo lines. And when you consider plane quartics, actually, the real locus of a plane quartic can be at most 4 ovals. It can be 1 oval, 2 oval, 3 oval, and 4 ovals, which are pairwise disjoint, or it can be 2 nested ovals. So you see, actually, we have many possibilities. But the claim of, in particular, we claim the theorem that in our case, the real locus is very special. It's just either 1 oval or 2 nested ovals. And same for the delta surface degree 2, defined of the real numbers. There are actually many topological types of the delta surface degree 2, defined of the real numbers. It can have various different topologies. But in our case, it's either a sphere or a torus. Very, very particular cases. Okay, so that's our theorem. And the concluding remark, I probably have to finish. So my concluding remark is the following. So we call these 2 types of involutions spherical Kovalevsky involutions and toroidal Kovalevsky involutions. As I mentioned in the theorem, they both fix an elliptic curve. They both fix an elliptic curve. And in fact, they are not conjugate. In fact, they're not conjugate. It's not difficult to show. Well, one of the standard tools for showing that is the Sarkisov theory, the one I mentioned before. I will not tell you what is the Sarkisov theory, but for those who know, I just say that the only thing that you can do on Delpets of degree 2 is a birational Bertini involution. You can blow up a point, make a Bertini involution Delpets of degree 2, Delpets of degree 1, and come back. And it's very easy to show that actually this operation, well, when you perform it of the real numbers, it does not change the real locus, because you blow up a real point, basically, which is a gluing of RP2, and then you also construct a real line, and somehow you get the same surface topologically. So you really cannot change the topology of the surface. So that's why involutions are not conjugate. And in our paper, we observed several phenomena like this. Somehow it led to a very sophisticated classification of involutions. So my main point was that we don't have this nice correspondence between conjugacy classes and isomorphism classes of the fixed curve. So this kind of a negative result. But still, I think it's nice to have such unexpected examples like Kovalevsky involutions, which appear only on the field of, well, which do not appear over the field of complex numbers, but appear over the field of real numbers. Okay, I think my time's up. I should stop here, and thank you for your attention.